Good morning. The next topic is the vector control of the induction motor. Basically, there are two types of control techniques are there. One is scalar control, another one is the vector control. Our stator voltage control, frequency control, rotor resistance control, etc. etc. These are all coming under the scalar control. Next one is the vector control. Actually, this vector control consists of a complete mathematical equation, and moreover the pioneer or the Guruji of the vector control is nothing but the DC motor control. So in case of the DC motor, we know the torque is directly proportional to the phi into I, right? Where your I is the armature current, phi is the flux. So your current in the DC motor, the armature current is responsible for the torque, and your phi is responsible for the speed. So if we want to control the speed of the induction motor, then we can able to control the flex. And if we want to control the torque of the induction motor, then we will control the armature current. And moreover, if we look at these two quantities, these two are quadrature to each other. So we are having two different decoupled quantities. Decoupled quantity means these two are not in phase, they are having the displacement of 90 degree, or otherwise they are orthogonal. So here we are having two different quantities. One is responsible for the speed, another one is responsible for the torque. In the motor, our main aim is we should control the speed as well as torque, and we are two different independent quantities for the control of speed as well as the torque. Now this is in case of the DC motor. Now coming to the AC motor, we are giving just only one supply, that is three-phase AC supply to the stator side, and we are having these two quantities in this three-phase AC supply only. These two are combined in the the component which is responsible for the torque as well as the component which is responsible for the current. These two are mixed together, and that is given to the stator of the induction motor. And now we have to separate these two quantities. In this three phase only, both the components are there. So if we are able to decouple these two quantities, that is the torque component as well as the flux component, then we can able to control the speed of the induction motor as well as the torque of the induction motor easily. So we should convert this three phase AC supply into the two quadrant. These two quadrants are, one is for torque, another one is for the flux, that is torque component and the flux component. So if we are able to convert this three phase into the two quadrant, then easily we can able to control speed as well as the torque. So இப்படி மாற்றுறதுக்கு பேர் தான், by converting the three phase into the two phase, that is known as the vector control. These are completely mathematical calculation. Already these calculation are available. So by using that calculation, we can able to control three phase into the two phase. Now let us compare the scalar control and the vector control. Actually scalar control is comparatively easy, whereas in the vector control is somewhat complex because it consists of complete mathematical calculation. And in the scalar control we are having the good steady state performance, whereas in the vector control, both steady state as well as in the transient, we are having the precise control, accurate control. And in the scalar side we are having the poor dynamic response, whereas in the vector control, since we can able to control in the transient as well as in the steady state, we can able to obtain the excellent dynamic performance. And scalar control is applicable for the low performance drive, whereas in the vector control this is used for high performance drive. And in the scalar, high power dissipation, whereas here low power dissipation. So since the power dissipation is low in the vector control, the overall efficiency of the machine will be high in case of the vector control. So in the industries maximum they will go for the vector control, right? So whereas in case of the low performance type, they will go for the scalar control, but for the precise control they are going for the vector control. But the thing is, the cost for the implementation of vector control is high when compared to the scalar control. And we know the analogy to the DC drive. So in the DC drive we are having two component, one is torque component, another one is the flex component. So here in the induction motor also we are converting the three phase supply into the two phase, that is nothing but D component and the quadrature, that is direct axis component and the quadrature axis component in the synchronously rotating frame. So in the vector control, we are having the two components. One is direct axis component, another one is the quadrature axis component. Your direct axis component is similar to that of the field current in the DC motor. So your IDS is responsible for the speed, whereas our quadrature axis component is analogy to the armature current. We know in the DC motor armature current is responsible for the torque, so our IQS is responsible for the torque. So IQS is known as the torque component, and IDS of the induction motor is known as the flex component. And once again, this is the analogy to the DC motor. In the DC motor, torque is directly proportional to the K phi into Is, whereas in the induction motor it is K into phi S into phi R, whereas your phi S is the stator current and your phi R is the induced rotor current. So we are just decoupling these two quantities. One is responsible for the torque, another one is responsible for the speed, which is also known as the flex component. And these are all the formulas. Now let us discuss about the block diagram of the vector control. So in the block diagram, initially the three-phase component should be converted into the two-phase component. For that we are having the Clark transformation and the Park transformations. So using that transformation, we are converting three-phase to the two quadrant, and then those two quadrants, they are compared with the actual current and the actual quantities, and once again it will be similar to the previous case. The error will be calculated, and the error will be once again it will be given to any one of the controller, and the actual control signal will be obtained. That control signal will be given to the thyristors, which are all connecting in the induction motor. So this is the basic principle of the vector control, and moreover, for you the detailed analysis is not necessary. Just the basic things are necessary for third year syllabus, whereas for the PG means you have to study in depth, whereas for UG this basic equation and the explanation of the block diagram is more than enough. So as a whole, the principle of the vector control is we are having that is the three phase will be converted into the two phase, and then that two phase component will be D axis and the Q axis. For that we are using the transformation, Clark transformation and the Park transformation. Actually the Clark transformation is used to convert three phase to the two phase, whereas the Park transformation is used to convert two phase to the three phase quantities. So these are all the general idea about the vector control. And this next one is the field oriented control. Actually field oriented control is nothing but our vector control, and this is the basic block diagram. And initially the three phase currents are measured with the help of the current sensor. Here they have sensed only the two currents. We know IA plus IB plus IC equal to 0. So by sensing only the two currents, we can able to obtain the third current also using this formula. And then the three phase quantities are converted into the two phase quantity, that is alpha into beta. It is IS alpha and the IS beta, and once again they will be converted into DQ component, because the stationary frame to the rotating frame, that's all. And then that is compared with the reference value. Already namakku theriyum we need how much amount of torque is required and at what speed the motor should rotate, and from that we should obtain the IS reference and the ISD reference also. Both the things we should calculate, and we should compare the reference value and the actual value, and then that is given to the PA controller, and the output of the PA controller will be the control voltage. And once again these two quadrant should be converted into the three quadrant, and then that three quadrant should be converted into the PWM signal with the help of the SVPWM, and the pulses are given to the three-phase inverter, and the output of the three-phase inverter is given to the AC motor. So this is the vector control of the induction motor. Up to that, the fourth unit over, and in the next class let us discuss about the fifth unit, that is synchronous motor drive. Thank you.